7-state process transition diagram. Last week also we discussed when we are going to do some process execution. So process contains 7 states. First one, create. That means new process is going to admit. We call new create. All syllabus we use the word create. New syllabus we are using new. Then once the new admission, new process state is coming, new execution is going to start. For example, 2 plus 5. So execution we are going to find out 2 plus 5 equal to 7. So that process we must insert in, we call it as fetch, insert, feed. We have to feed the data to the execution. So while starting the state, we call as new. Then ready state, ready and suspend. If the space of the random access memory is not enough, we have to move that state into the virtual memory. Earlier, last day also I said, if you are playing a game, if the random access memory capacity is not enough, then virtual memory compensate the space for the purpose of the random access memory. So it provides you the temporary memory, okay, from the hard disk. So hard disk contain 1 TB or more than that space, but when you are playing game, for example, your game is around 9 GB, your random access around 8 GB. So 1 GB space is not enough, 1 or 2 GB space is not enough. So therefore, virtual memory, that means hard disk, provide the temporary memory. We call it as virtual memory. So in such situation, if the space is not enough in the random access memory, admitted process state is moving to the ready and suspend state. So swap out and waiting is moved the swap out and waiting. All syllabus we use the keyword swap out and waiting. New syllabus we call it as ready and suspend. If you are doing past papers, you need these words. Then while the process is executing, where is the process execution happening? In the ALU, execution is happening ALU. Who is in charge of that? Random access memory. So random access memory is the one which provides which fetch the data or instruction to the control unit, then from the control unit to ALU. So every time the RAM is in charge there. So execution is happening inside the arithmetic and logic unit. Then there can be some interruption, badava. So as a result of interruption, the order may change, processing order may change. So some process states has to be blocked and wait, has to block until the high priority execution is happening. Then after complete the execution, move to the exit or terminate. All syllabus we use the keyword terminate. Now we are using exit. And while executing happening, if the random access memory space is not enough or higher priority process is executing, that situation we have to block and suspend to the virtual memory again. We call it as swap out. So from the virtual memory, coming to the random access memory, we call swap in. Moving to the virtual memory, we call as swap out. So for these 7 states, last day we drew this diagram. So new is going to admit with the help of long-term scheduler. Okay, so the order is going to schedule with the help of long-term scheduler. Long-term schedulers are the programs. So it schedule and move the new state into the ready state inside the random access memory. So provide the space for the that ready state in the random access memory. If the RAM space is not enough, it will move to the virtual memory. So red color covered area is virtual memory space. So admission can happen to the random access memory. If the space is not enough in the random access memory, it may move to the virtual memory. So we call it as ready suspend. So once it is in the ready suspend, when the space is available in the random access memory, from the virtual memory to random access memory, the ready state move, we call it as activate. And sometimes if the space is not enough in the ready state in the RAM, it may move to the virtual memory. We call it as suspend. So activate suspend is happening in between random access memory and the virtual memory. So in such situation, medium term scheduler is in charge of that. That's what I wrote there, MTS. Can you see? Then in the when it is in the ready state in the random access memory, execution can happen. Execution means running. So we call ready to execution is dispatch. Ready state to execution we call as dispatch. So while executing, there may be timeout. When, for example, Zoom lesson, now it is executing for us, but after 40 minutes, it will time out. Okay, so timeout means again move the ready state or exit. So here, the normally Zoom lesson is exit. It's start, stop it. Okay, so if there is a program keep on running, then it will move the ready state. Then this process, dispatch and timeout, that means not without executing, if it is moving to ready state, this process, that means dispatch and timeout, controlled by the short-term scheduler. So STS, I use the keyword, that is short-term scheduler. When you are writing, write it in full format. Okay. So after completing the execution, it is released to exit. So the space which allocated for the running state, again reallocate for the next process. Why? When the program execution finished, the space is allocated for the another process. Okay. So while executing, event wait, that means interruption can occur, hardware interruption or software interruption. As a result of interruption, the order of the process may change. So it will move the block state. So block state inside the random access memory. Then if the space of the block, if it is moving to ready state, after event occur. Now I am using the PowerPoint. So if I need to start another file, and I can think I am using PowerPoint and Internet Explorer. So I'm stopping the Internet Explorer at this moment and use the PowerPoint. So I have already made the interruption for the Internet Explorer and for the Edge, and I'm using the PowerPoint. So if I want to reuse the Edge, I can give the event occurring for the Edge. So it will move the ready state. If it is in the block state, move the ready state. And if the space is not enough, it will swap out to the virtual memory. We call block suspend. So we call it as suspend. Swap out means suspend. So if the space is enough, it may come to the block state inside the random access memory. We call it as activate. So the moving to the virtual memory and to the random access memory, both the side is controlled by the memory medium-term scheduler. MTS, I wrote the medium-term scheduler. When you are drawing the diagram, don't write the short terms. Write it in full format. Medium-term scheduler, long-term scheduler, short-term scheduler. I don't have the space. That's what I wrote here in short form. So block suspend to ready suspend, move with the help of event occur. Then we are going to discuss about the new create. It is the first state of the 7-state diagram. When the process is start, it is admitted from the create new state. So when the new process is starting, it is admitted from the create new state. Process of this stage should be wait until the permission is granted for the ready state. So waiting until the ready state is falling into that. So until it get the permission, it will wait the new create state until calling to the random access memory. It has to be there in the outside. That means waiting in the new create state. The admission of the new state to ready state is controlled by the software called long-term scheduler. It is controlled by the long-term scheduler. Okay. So then ready state. Ready state means where is a ready state? That is in the random access memory. When the process is admitted to the random access memory and state is called ready state. So that state we call ready state. it is ready for execution. That means running, it is ready for the execution. The program may consist of many processes, therefore may be many read process at many ready process at any point of the system execution. Just look at that point. The program consists of many processes. Program may consist of many processes. Therefore, there may be many ready processes at any point of the system execution. So at any point of the system execution, there may be many ready states. So if the RAM space is not enough, then it may move into the virtual memory as well. For example, in one processor system, only one process can be executed at any time. One processor execute only one process, then and all the other concurrently executing process will wait for the execution. So concurrent simultaneous processings are there to execute in the cores. Earlier we discussed there are cores in the processor. Processor is partitioned into many cores. There may be 4 cores normally in normal i3 machine. Then if at one time only one core, that means at one time one core can process one cycle. Okay, if there are 4 cores, 4 cycles are processing at same time. 4 cycles are running at the same time in 4 different cores. Like 4 classes are executing at the same time. එක වෙලාවේ පන්ති 4ක් run වෙනවා. හැබැයි එක පන්තියක පන්ති 4ක් run වෙන්නේ නැහැ. වෙන වෙනම course වලයි execute වෙන්නේ. So if your machine is powerful enough, then it will do more functionalities. It may show 12 threads or 6 cores like that. If the ready state waiting for execution until it gets idle to run this call context switching. If the ready state waiting for execution until it gets the idle, run is called context switching. The process දෙකක් execute වෙන්න තියෙනවා නම් ඒ දෙන්න අතර මාරුවෙන් මාරුවට කරනවා. මාරුවෙන් මාරුවට කරනවා කියන්නේ එකක් කරන ගමන් අනිත් වැඩේ කරනවා. ආයෙ ඊළඟ වැඩේ. ආයෙ අනිත් වැඩේ. එතකොට දෙක අතරේ මාරුවට කියන්නේ context switching. හරියට ෆෝන් එක තියාගෙන text messages කර කර note එක ලියනවා. context switching. හරි. process එක තනි single process එක වැඩ දෙකක් එක වෙලාවෙ කරනවා වගේ. If a computer has only one processor, then it can operate only one process. Therefore, there may be several processes which are in the waiting state in the main memory. So there may be many processes waiting in the random access memory. So, but modern computer can process several tasks at the same time as a result of cores. Is this clear? If you have any issues, just let